Class recording started, as you can see. So yesterday, we started in on section 2 of chapter 6, and we were supposed to introduce 4 concepts yesterday. We only got to 2 of them. The last 2 are pretty fast at the end. We got the 2 big ones. So the first thing that we introduced yesterday was the idea of kinetic energy. We said that kinetic energy is energy based on what? Movement, right? That if something is moving, it has the ability to change or make things different than they were before. This ball, as it sits here on the table, can't really do much of anything because it's not moving. But if we apply force to it, do work on it, get it to move, then it now has the ability to move or change other stuff. We spent a good deal of time looking at the formula for kinetic energy, right? 1/2 mv squared, showing us that the kinetic energy of an object is dependent or affected by 2 things, that object's mass and its velocity. And we said that kinetic energy is directly related to the mass, but it's quadratically related to the velocity, right? Meaning that if the velocity goes up by 2, there's not twice as much kinetic energy, there's 4 times as much kinetic energy, right? Because of that squared factor. The next thing that we talked about in class was the work-energy theorem. And the work-energy theorem states that if we do work on an object, the energy of that object will change. How much? Depends on how much work we do. The amount that the energy of the object changes is equal to the amount of work that we do. And that's important when we talk about how much work, how big of a force, how big of a distance do we apply that force to this object, how much work is done, that will cause a greater change in energy or a lesser change in energy based on the amount of work. Okay? Good there. All right. The sheet I gave you today is a sheet of questions that are actually from the end of chapter 6 in your book. So these numbers relate to chapter 6. These are all questions at the end of chapter 6, but I wanted to spend some time in class and go over them because they're important ideas. So the first question, number 79 here, gives you information about 4 different joggers. It gives you different masses and different speeds. Now notice it didn't give you any numbers, it just gives you how those masses are related to one another. So, the question asks, rank the joggers in order of increasing kinetic energy. So based on these values, I ask you, which of the joggers has the greatest kinetic energy? Okay. Now, I want this to take us about a minute or so. So you might not have time to do all the calculations, but you should be able to make an educated guess based on the factors that we talked about that affect the kinetic energy. So, take an educated guess about which of those joggers is going to have the greatest amount of kinetic energy. So which of these joggers has the most kinetic energy? Jogger A, jogger B, jogger C, or jogger D? Based on, we talked about some of the factors that determine the kinetic energy of an object. those are probably the two answers that people would give most often, and there's reasons why, right? Why would some people say that jogger D has the most kinetic energy? Any ideas based on the information? It has the most mass, right? But a lot of people said jogger B because greatest speed, right? Correct answer here is going to be jogger B, all right? Because, right? Margo, did you pick D, I'm assuming?
Yeah.
All right, so why, if we look at the formula for kinetic energy, right, there's two factors, but which of those factors affects kinetic energy more, the mass or the speed?
Well, I guess speed.
Because why? What are we doing to speed in that formula?
What's the formula?
Over here on the left, by the flag, right, up in the top.
Oh, we're squaring.
You square that velocity,
makes
right?
sense. All right.
So even though we may not have done a bunch of calculations on that, or we didn't have to go through with those calculations, we can make an educated guess that B has the most kinetic energy because its speed is the fastest. Okay? This is the kind of question, I know you guys aren't taking an AP test, but this is the kind of question that shows up on AP tests, that shows up on like ACTs and stuff like that, where there are no numbers, we're just looking at the factors, right? If the speed goes up, that's going to increase the kinetic energy, et cetera, okay? Good there. The next question is not on your sheet, but is related to one of the questions on your sheet. So it says, two identical cars are traveling on the road with the same speed in different directions. Which of the following statements is true? Both cars have the same kinetic energy, both cars have the same kinetic energy, but one is positive and one is negative, or the kinetic energy of the cars is different. So this question, like I said, isn't on your sheet, but it's related to one of the ones on your sheet. So, two identical cars traveling on the road, different directions, same speed. Which of the following statements is true? Same kinetic energy, but one's positive and one's negative, or kinetic energy is different. All right, correct answer to this question is both cars have the same kinetic energy. Ashley, go ahead.
I answered A, but is it possible for kinetic energy to be negative?
That's actually on your sheet, actually the question that's related to it, number 80 asks that same question, right? Is it possible for kinetic energy to be negative? Okay, so good question. The answer to that question is no, okay? We said kinetic energy is based on movement, right? It's energy related to motion. So either it's moving or it's not moving. So it either has kinetic energy or it doesn't have kinetic energy. Does that make sense, Ashley? So it's either 0 or it's some number, okay? We talked about yesterday that kinetic energy is a scalar quantity, right? It doesn't have direction. And another way that we can sort of explain it too, in the formula, we're squaring velocity. So even if we put a negative number in for the velocity there, mathematically, what's it going to turn out to be? It's going to be positive. Okay? Did I answer your question, Margo? Good.
Yeah, I was going to ask if this, because I remember something being scalar. I didn't know if it was this or something else.
Yeah, the kinetic energy is scalar.
Yeah.
Okay. All right, good there. Okay. Next question. The next question is number 81, which shows up at the bottom of the page here. So 81 says, the work required to accelerate a car from 0 to 50 is W. Again, no number there, just looking at factors, right? So part A says, is the work required to accelerate the car from 50 to 150 equal to twice the original value, 3 times the original value, 8 times the original value, or 9 times the original value? This question is very similar to a question that we talked about right towards the end of class yesterday. So, is the amount of work to go from 50 to 150, twice the original, 3 times the original, 8 times the original, or 9 times the original. If you want to talk to the person next to you and kind of, throw some ideas off of each other, feel free to do so for this question. This is definitely a talking point. Okay? So if you want to discuss with somebody before you answer, feel free.
Confused.
Oh, gotcha.
So this question is very similar to a question that we did towards the end of class yesterday.
Did you put these questions in yourself?
What?
Did you put these questions in yourself?
Yeah. I mean, this question is actually straight up from the book.
Yeah.
But I have to type it. I have to type it into the website. Yeah. Why? Do you not like the way I worded it, Wargo? Or?
No, I just was wondering if there was different social studies or
No, this
physics.
is just a generic website that you can I could type in what's your favorite animal, dog, cat, horse, or hippo, and we could do that.
Do you have to pay for it at all, or no?
No, I have a free account, yeah.
Okay.
But if I paid for it, I could get more responses per poll, but I also could track answers, so I could find out which one of you is actually sending what answer. So I could use it in
So we do tests on this?
yeah, so I could grade it basically,
Oh.
Do that.
find out exactly who is, answering questions this way or who's answering questions that way. All right, so let's take a look. Okay, so, all right, we're pretty spread out here. Okay. Before we talk about what the original answer, or what the actual answer is, you guys want to know the actual answer first?
Yeah.
Or talk about why? The answer is 8.
Oh.
So, let's go here, okay? All right, let me grab this and put it here. Okay, so yesterday we talked about this scenario, right? Where the car was accelerating from V to 2V, and we looked at the changes in kinetic energy. In increasing the speed from V to 2V, right, that took the kinetic energy from 1 to 4. Because remember, we have to square the velocity, right? With that same idea, let's take a look at this case, right? So we need to keep track of 3 things in this problem: velocity, kinetic energy, and work. So, how does this car start? 0. It says starts at rest, right? So its initial velocity that we have is 0. And then it says it goes from rest to 50 kilometers, meaning that the second velocity we have is 50. And then a little bit later on, it says it goes from 50 to 150. So the next velocity that we know about is 150. In keeping track of the kinetic energy, at the beginning, if something isn't moving, how much kinetic energy does it have?
0.
0. Here, it doesn't tell us anything about the mass of the car, so we can't really calculate the amount of kinetic energy it has, but we know that it has some value of kinetic energy. We'll call it KE, because we don't know exactly what it is, but it's got some. Now here's the trick to doing this problem. In going from 50 to 150, how much of an increase in speed is that? It's triple the speed, right? Going from 50 to 150, that's 3 times bigger. But if the velocity increases by 3 times, how much will the kinetic energy increase by? 9 times. So this is now 9 KE, right? Because what are we doing to the velocity in that formula? Squaring the velocity. This question is asking us about work. We learned in the first part that work is equal to F times D, but this problem doesn't give you anything about force or distance, so we can't use this. But we learned yesterday that we can determine how much work is done if we know how much the kinetic energy changes. So in order to determine the work, you can't just look at one place, you have to look at the change from one point to another. So from here to here, this does an amount of work equal to KE. Right? If we do this, right, work is equal to final, which is KE, minus initial, which is 0. Does that make sense? But then going from here to here, right, work is equal to KE final minus KE initial, right? That's what delta means. So this is 9 KE minus KE. So the amount of work that we did was 8 KE. Good. That make sense? This is probably the hardest multiple choice question that I could give you on the test. Now, with that being said, you've seen 2 questions like this, yes? Okay? Any guess where you might see the third time? Maybe you might see this question on test, right? So maybe next Thursday night, take a look over this and make sure we understand these things. Okay? All right, good there? Yesterday, we did not get to the last 2 topics that we were supposed to deal with, so let's cover them quickly. All right, let's go here. All right. So this goes back to the packet that I gave you yesterday. So let's switch gears for a second and take a look at the packet that I gave you yesterday and finish up these topics. So in this picture, this girl takes a bowling ball and she lifts the bowling ball from the floor to the shelf. Granted, it doesn't have like a case or she doesn't put it in a rack or anything. She just puts a bowling ball on the shelf, which doesn't seem real safe, but whatever. Yep. Does she do work on the bowling ball?
Yes.
Sure. She applies a force. The bowling ball moves because of that force. That's work. But earlier, we talked about the idea, work energy theorem, that work is equal to the change in kinetic energy. How much kinetic energy did the bowling ball have down here before she moved it?
0.
0. And now that it's up here, how much does it have? Is it moving as it sits on that shelf? No. So it went from 0 kinetic energy here to 0 kinetic energy here. That doesn't seem like work based on this definition. But what we find out is that sometimes that energy has to go through like an intermediate step before we get the kinetic energy out of it. And we refer to that kind of intermediate step as potential energy. Whereas kinetic energy is energy of motion, potential energy is energy of position or location. that object has the ability to change something because of where it is, not necessarily what it's doing. There are two kinds of potential energy that we concern ourselves with. One type of potential energy is due to gravity. We refer to it as gravitational potential energy. Gravitational potential energy is where an object is relative to a source of gravity. Usually the source of gravity that we're concerned with is what? What's the biggest source of gravity that dominates our lives?
Sun.
The sun doesn't really dominate our lives. It is. What?
It keeps us alive.
Yeah, but we're so much closer to the Earth. The Earth's gravity affects our lives much more than the sun's gravity. Yes, actually, if we look at the actual force of gravity that the sun has on us, it's pretty significant. But because we're so close to the Earth, it plays a bigger role, right? When we talk about direct force and stuff like that. So, here, we calculate the gravitational potential energy of an object based on three things. The mass of that object, the acceleration due to gravity. Here on Earth, that number is actually going to be what? 9.81, just like it always is. And then the last factor is a height factor. How far away from the Earth are we? That's going to play a role in how much energy that object potentially has. Okay? Good? If we take a look here at this situation, right, this guy climbing a mountain, it says a candy bar called the mountain bar, right, has a nutritional energy content of 8.87 times 10 to the 5th joules. We don't measure our food in terms of energy content of joules. We use a different unit, right? We use what? Calories. Calories are just like an English unit for energy, right? Kind of like feet and meters and stuff like that, right? So, when we talk about the amount of calories that are in a substance, we're talking about how much energy is in it. In this problem, our mountain climber, who has a mass of 81 kilograms, is turning the energy of this candy bar into potential energy. So it says, what altitude gain can the climber achieve? Altitude means we're going to be measuring, Sam?
Height.
We're going to look for height, right? That's what we want to end up looking for. How high can this climber actually climb? They gave us the mass of this climber, 81 kilograms. And the nutritional bar has an energy content of 8.87 times 10 to the 5th. But we want to convert all its energy into potential energy. So that means PE, and we use the subscript G to represent the gravitational potential energy, is going to be equal to 8.87. Let's just turn that into a decimal or an actual number. 887,000 joules. And then, right, we just learned that the gravitational potential energy of an object depends on three things, mgh. So we start plugging things in, right? 887,000, okay? Joules equals the mass, which we know was 81 kilograms. We said that G here on Earth we know is what value? 9.81 meters per second squared. And then that leaves us just with H. So, you can calculate H here. Anybody running that through their calculator yet to get an answer? Try it.
I got 1,116.27.
You good with that?
What?
1,116.27.
1120.
What is it?
1120.
Oh, so. And then that'll be, okay, and that'll be measured in meters, right? Then going back here, 3 significant digits in the mass, 3 significant digits there. So we would round that then to 1120 meters, which is pretty high. If you figure that there's a little bit more than 3 feet in a meter, that means that he's climbing, I don't know, about 3,500 feet on one mountain bar. So
Like
A
that's-
candy bar. It was candy bar.
no.
Isn't it 5,000 to?
Yeah, but this is like 3,500 feet. It's about half a mile, I guess.
Oh.
So he goes, I mean, but climbing upwards half a mile is pretty, that's, you know, pretty good. Okay. All right, good there? The last kind of potential energy that we talk about comes from elastic materials. If we take an elastic material, like let's say this rubber band, right? And we stretch it out, what is that elastic material trying to do? If I stretch it this way, what is it trying to do? It's trying to go back to the way it started, right? If I let it do that, now I can use that elastic material to shoot little wads of paper across the room, or flick your friend in the arm, or whatever, shoot water balloons across the, or shoot yourself in the face with your ID, whatever it is, okay? We refer to that energy as elastic potential energy. The amount of elastic potential energy in an object is affected by 2 factors. It's affected by how far do we stretch that object. Also could be compression. So if we talk about like a spring or something, like in a dart gun, if you crunch the spring down, okay? But it's also affected by a factor that we call the spring constant. The spring constant is a property of the material that we are stretching or compressing. So this rubber band has a spring constant, and a bungee cord has a spring constant, and a trampoline has a different spring constant, and the springs that make up the coils on your bed has a different spring constant. So that's just a property of the material. That's going to affect how much energy it can apply to an object. Okay? Good there?
Yeah.
All right. Thursday, we're back on lab. And then Friday, we'll pick it up with conservation.